Okay. Uh, yeah, welcome everyone to today's row. We have two speakers today, um, which have very similar topics. So it's a quite new, interesting perspective on robust optimization. So the first speaker is Sarah Wajsbrot, who is a PhD student at the University of Lorraine. She did her bachelor and master in mathematics at Sorbonne University and another master specialized in optimization at Paris-Saclay. And her research focuses mostly on robust multi-stage optimization, geometric optimization. And the interesting part is that there are techniques from computational geometry coming in. So very happy to have you here. Please, Zaha.
Okay. So, hello everybody, and thank you for inviting me to this webinar. So, I will talk about a result about the complexity of an optimization problem called k-adaptability. And this work is also readable here on this article about affine families of polyhedra. So first, a word on complexity of linear programming. So what I will discuss is a theoretical result. And so I will need to define the following notion, which is strongly polynomial time algorithm. So what is a strongly polynomial time algorithm? It's an algorithm where you can control the bit size of the computation. So not only it's polynomial in the Turing machine, but also um, you want something only polynomial in the number of input parameters and not their size. When you look at the real RAM, if you can bound the bit size of the computations, you have a polynomial algorithm, you automatically get something strongly polynomial. Another way also to obtain this is through the model of computation of algebraic decision tree. And a big question in operation research is the question of strongly polynomiality of linear programming. And it's one of the SMAIL's problem for the 21st century. So it's an open question. And what we know about linear programming is that the methods, such as interior point or ellipsoid, are polynomial but not strongly polynomial. No, we don't know. And the simplex method, there are no lower bounds proved. But there is still hope in a sense, because when you fix the dimension, which is something that happens often in computational geometry, then you get a strongly linear time algorithm. And this is due to Megiddo and an algorithm from the 80s. So the problem I will talk about is coming from a sort of approximation of two-stage robust optimization, which I will call now. So in two-stage robust optimization, you take a first decision x, then some parameter is revealed, some uncertain parameter is revealed, and then in the second stage you adapt to it. So you have more freedom. Your y here is here to adjust. And so it has many applications, antenna design and others, but it's known to be difficult. So for instance, there is a NP hardness result from Gus Litzer. Even for quite simple cases. So for instance, when the recourse, so the matrix B, is constant, doesn't depend on omega, and when the polytop, and when omega, the uncertainty set, is a polytop that is described by linear inequalities. And in order to still make progress on this problem, one solution is to replace the variable y by affine policies. So it means you don't optimize on any possible second stage decision, but it will depend affinely on omega. Another way is it will depend piecewise constantly on omega. And this is where you obtain k-adaptability. And if you want exact solutions, then you can do it, but under really restrictive conditions. Now, if you look at k-adaptability, so it was introduced to approximate mainly this two-stage robust optimization by Bertsimas and Karamanis. And here, what you do is first you take first-stage decisions, and it consists in x and k vectors y1, yk. Then so the uncertainty parameter is revealed. And then in the second stage, you just pick the best among k vectors to adapt to this omega. And so in terms of complexity, it's shown to be NP hard when the dimensions are in the input, and omega is described with its extreme points. And there are some polynomiality shown, but also on really restrictive conditions and not strongly polynomial. So note that the existing results always consider a recourse matrix constant. And so what we wanted to look at was, can we say something when B depends really on omega? So I'm going to define two more. Yeah. And you have solution schemes that exist, but again, for special cases. So first, to work on this problem, we eliminate the x. We eliminated the x. So I'm just taking k vectors y, and I kind of delete the x vector. So this we will call k-adapt. And it has a decision version, which is given the m, so it's the number of rows of my matrices or the number of constraints, and some affine maps, can I find k vectors such that for any omega, at least one of them adapt to this omega. So this will be the decision version of k-adapt. So now we are ready to present the results concerning these two problems. So first, when the uncertainty set is a segment, and I look at the k-adaptability without the first stage decision x. And when I fix the dimension of the variables and I fix also k, then we have a quadratic bound for the decision. And in the same setting, we have a quartic bound for the optimization. So this is really interesting because the exponent in M doesn't depend on the dimension D or K. So we obtain fixed parameter tractable algorithms with respect to the dimension. And in a second time, we looked at the problem where omega is of any dimension, so not anymore a segment. And then what we show is that when, again, you fix the dimensions, there is a strongly polynomial sum algorithm in the number of constraints, but you see that the exponent here does depend on the dimension and k, and the techniques are coming from computational algebra. All right. So now what I want to do
Zara,
is,
one question maybe for clarifying. What do you mean by complexity of a polyhedron?
so it's the maximum between the number of vertices and the number of inequalities, depending of how it's, and also the dimension where it lives.
Okay.
And yeah. So what I will do now is to give you more insights on the first result. So we look at the case where the dimension of omega is 1. For this, I need to introduce some notions to explain the techniques. So first, algebraic decision trees. So a decision problem is modeled by an algebraic tree. If your decision problem take as input a vector, and you have a tree, and this tree is labeled with nodes. Yeah, has nodes, and the nodes are labeled with predicates, which are polynomials. And now to execute your decision algorithm, you have to go through the tree with your input vector, and at each node you evaluate the predicate at the in the vector, and you branch depending on the sign. And so the leaves are labeled with true or false, and so you obtain the answer to the decision problem going through the tree like this. You have a tree for each size of input, and the degree of all the predicates are bounded. The runtime will be just the height of the tree. So an example, for instance, testing the rotations of 3 points in the plane can be modeled by such a tree. The second thing I will need is a monotone to define what is a monotone problem, decision problem. So imagine you have a decision problem that depends on a parameter, lambda. We say that it's monotone if whenever it's true for some lambda, it's true before. It's true for smaller lambda, smaller reals. So for instance, here we have a problem where we fix a center and we are in input a set of points, and we want to know if there is one point that lies outside a circle of radius lambda. So if it's true for some lambda, then if you shrink the circle, it remains true, so it's monotone. And with these two notions in mind, we are ready to see what is parametric search. So parametric search takes a decision problem that depends on the parameter. This decision problem should be monotone in lambda and modeled by an algebraic decision tree. And when you have these two elements, the parametric search gives you lambda star, which is the largest possible lambda, such that your decision problem returns true. So a few elements about this lambda star. It should be a root of one of the predicates. So greedily, we could just compute all these roots and run them in the algorithm and take the best possible. But it's too long because you have an exponential number of predicates. And so parametric search is really useful because it only squares the complexity of the decision algorithm, which is the height of the tree. And also it stays eligible for parametric search. More precisely, how does it work? So imagine you have an interval I that contains your lambda star. And what you're going to do is you're going to go through the tree with this interval. So in the first node, you take the interval, if you compute the roots of the predicate, and you run the roots in the algorithm to determine what is the best root, the largest root, such that it returns true, and the smallest root such that it returns false. And then you update your interval to be this smaller interval. And you follow the branch depending on the sign, because then your predicate is of constant sign between the two roots. And you go through the tree like this, And either you cross at some points lambda star, or you ended a leaf. You ended a leaf, and you just take the supremum of the interval. And so it squares the complexity of the decision algorithm, because you have to go, at worst case, you have to go through all the I to the tree. And at each node, you have also to execute the decision algorithm on the root. So with this in mind, we can now apply it to k-adaptability. So let's see how. So first, the sake of the presentation, I will just do it for two adaptability, but it works exactly the same way for nk. My omega, I take it to be 0, 1, and the dimension of the variable is fixed. So to adapt the decision is the problem here. Can I find two vectors, y1, y2, such that whatever uncertain parameter occurs, one of the two vectors adapts to this omega. So this is just decision version of two adaptability. Now I also need to introduce this one adapt, which is in fact the classic robust optimization feasibility non-adjustable. So here I ask, can I find one vector that adapts to all the omegas in a certain segment? And due to the convexity of the functions in omega, this is equivalent to asking to solve one adapt on the discrete set alpha beta. And this is done by linear programming. And here we can use one algorithm by Megiddo, which is linear and can be modeled with the algebraic tree model. So how one adapt is used to solve two adapt? We are going to introduce a function sigma, which takes a real parameter and asks for the largest possible value such that there is a solution to one adapt on the interval. So until where can I go to the right to still have a solution that adapts to all these omegas? And I can do it define it for any t. And an interesting result is the following. So to adapt, the two adaptability decision returns true if and only if iterating two times sigma going from one extremity of the segment gives you the other extremity. And when you replace 2 by k, by any k, so we'll just iterate k times. So how can we use it? Well, computing sigma of t for a given t is in fact computing the optimal value of a linear monotone problem that is the decision version of a linear program. And we've seen just before that there is a linear time algorithm for this. So we have all the ingredients to apply parametric search to a linear time algorithm in the number of constraints, and this gives us the quadratic bound. So here it remains true for any k, because all you're gonna do is just iterate it, and since you fixed k, it doesn't change the complexity. Okay. So now, can the same arguments be used for higher dimensions? We don't know, but we can use some other tools up to now. So what about any fixed dimension of the uncertainty set? I recall the decision version in for any k, and here I consider omega of any fixed dimension. So this problem reduces to testing the emptiness of a semi-algebraic set. Indeed, when you look at the feasible region of k-adapt, it's the set of y in KD, such that for all omega, a certain formula that depends on some polynomial is true. And so here we use techniques from the following book from Bazou, Pollack, and Roy. So quantifier elimination, to eliminate this for all omega, this universal quantifier. And this quantifier elimination can be done in polynomial time in the number of polynomials of the formula. So this is all due to fixing the dimension. And then we can also use another algorithm that tests the emptiness of a semi-algebraic set. And here we have a quantifier-free formula. So we don't have anymore the universal quantifier. So these are quite general tools, and this gives us the bound you see here, which is big, but at least allows us to prove something polynomial in M. And lastly, I wanted to talk about the geometry behind the optimization. So when we define a feasible region, here we saw it's a semi-algebraic set, but more precisely, I'm going to need first to define a heating set, the heating set problem. So when you have a family of geometric objects, what is a heating set? So here, I want to find points that together pierce all the triangles. So for instance, I can put a point here. It pierces the three triangles. And I can put a second point here. It pierces two triangles. And here it pierces triangles. So here I have found 3 points that together pierce all the triangle. So what I mean is that for any triangle I take, there is 1 point in my heating set that belongs to this triangle. This is a heating set. And this is a really classic problem in computational geometry to ask if there is a heating set of given size for a certain family of geometric objects. And if we look at k-adapt, and for each omega, we can define the following polyhedron, which is the set of y that adapts to the given omega. So when I say adapts, it means verifies the inequalities in omega. And then, so it is a polyhedron. And then I can define P of big omega, which is the family of all these polyhedra indexed by omega. And now we observed that the decision version of k-adaptability is actually a heating set problem for this family of affine polyhedra. And it gives new tracks and new problems, in a sense, because, well, we can just go to computational geometry and look at the problems that are classic and see what happens when we replace the discrete setting with this continuous setting. And so, and it also shows, it also allows to build bridges between those two fields that are operation research and computational geometry. So I will, yes, some pictures. These families of polyhedra, they can look at this, for instance. So here you have a segment for omega, and you have three constraints. So you have to imagine a continuous motion. And the right, you have two-dimensional omega and four constraints, so quadrilateral. And the question of feasibility is, can I find k points that hit my triangles or my quadrilaterals? So I will conclude. What was this talk about? So first, when you fix the dimension, you can obtain tractability. Second, parametric search is a technique from the 80s that allows to optimize some specific problems by only squaring their complexity. And with this in mind, we can apply it to k-adaptability, decision version, and obtain quadratic and quartic bound for optimization. For larger dimension of omega, this is not the case anymore, but some other tools from computational algebra give strongly polynomial bound. And for the perspectives, can we say something if k is in the input? Can we obtain some fixed parameterable tractable algorithm for at least dimension 2 for omega, for instance? And the tools from computational algebra could be maybe more tailored for the bilinear setting that we are in. Thank you for your attention.